If you're evaluating 3D Gaussian splatting using the standard MIP NeRF 360 protocol, you might be measuring the wrong thing. Every paper holds out every eighth frame, but on a smooth camera trajectory, those held-out frames have trained neighbors on both sides. You're not testing spatial generalization, you're testing near-trajectory interpolation. A new study introduces a fair match count protocol to isolate this effect. They compare holding out frames spread evenly versus a contiguous spatial sector, keeping the training data count identical. The result? A massive interpolation extrapolation gap of 3 to 12 dB. This isn't noise, it's a systematic bias. Crucially, this gap is larger than the performance differences between competing methods, which typically hover under 2.5 dB. In some cases, switching to spatial holdout actually flips the method ranking. Why does this happen? The gap is dominated by a diffuse geometry proxy component, accounting for 62% of the loss, with the remaining 38% coming from spherical harmonic overfitting to training view directions. Higher SH degrees can actually hurt extrapolation. To prove this isn't just a Gaussian artifact, they tested Instant-NGP, a volumetric NeRF with no Gaussians or SHs. The gap persists, correlating at R equals 0, 90 with the 3DGS results, confirming this is a fundamental data coverage problem, not a representation-specific one. Regularization techniques like Gaussian dropout only yield marginal gains, proving this is a data problem, not an optimization problem. The fix: coverage-guided view selection. Adding just one view far from existing cameras improves extrapolation significantly. For the community, the takeaway is clear. Standard holdouts are useful for near-trajectory rendering, but if you claim spatial generalization, you must report a spatial holdout metric alongside the standard one.